Hi friends, welcome to Easy to Learn channel. So in this video, I am going to explain about the architecture of 8086 microprocessor. Here the entire architecture which is divided into two different parts. The first part is a bus interface unit and execution unit. Here the bus interface unit contains the circuit for physical address calculations and a pre-coding. There is an instruction stream byte queue which is of 6 bytes of size and a control system. So here that means the total bus interface unit which consists of all these three. Whereas the execution unit which consists of a special function or general purpose registers, GPS, general purpose registers, pointer and index registers. These are the pointer and index registers, and arithmetic and logical unit, and here is an arithmetic and logical unit and different flags. So here first we have to see about bus interface unit, that is first one is a segment registers. So here these segment registers, the total registers in 8086 microprocessors are general purpose registers, segment registers, pointer and index registers, and flag registers. So we call it as 8086 microprocessor registers or register organization of 8086 microprocessor. Now let us see in the bus interface unit. Here is an instruction system byte queue first. So this instruction system byte queue is nothing but, so here there are different 1 2 3, there are 6 numbers are there here. So in these 6 numbers are nothing but each byte, that means 6 bytes of instructions. The first byte, for example, there is an add instruction, sub instruction, mul instruction, in instruction, and in instruction, and push instruction. So here there are 6 different instructions are there. That means, so if you run this 8086 microprocessor, the first instruction will be first add is executed here. After execution of this add, the sub instruction is moved to first byte of instruction, and mul instruction is moved to second byte, and the push instruction is moved to fifth byte, and sixth byte is empty. Then again one more instruction is stored. That means, so it stores a 6 bytes of instructions. So what is the use of this instruction stream byte queue is, so in order to speed up the operation of the microprocessor, so here 6 bytes of instructions, no need to wait for the execution. So it is done parallelly, execution is done parallelly. So here all these instructions are executed based on the system byte queue. Here total 6 bytes of instructions are stored. In order to speed up the operation of the microprocessor, we have to store 6 bytes of instructions. So that is the use of instruction stream byte queue. So let us see, next one is segment registers. Okay, so in this segment registers, which consist of extra segment, code segment, stack segment, and data segment. So here the memory size of this segment register is 1 byte, total 1 byte. That means the total memory of this one is 1 byte. So whereas each segment is it stores 60 kilobytes of instructions. Each segment is a 64 kilobytes. So and it is having a and it is having the range of 0000 to FFFF. This is 16 bytes. So we have to generate a 20-bit physical address. How to generate a 20-bit physical address means, so here we have a segment address and then we have a offset address. segment address and offset address. Here the segment address is, for example, if you take a segment address as 1111 and offset address is 0001. So this is an offset address location. So we have to shift, that means segment address we have to shift, that means segment address is what, 1111. So that means how to write in a 16-bit form, 0001, 0001, 0001 and 0001, right? Next, we have to shift this segment address 4 bits left. We have to shift, and if you shift left side, right side is added zeros. That means here we have to shift 4 after shifting of 4 times, 001, 001, 001, 001 and remaining 4 zeros. We have to shift left by 4 times. Next, offset address. So we are taking offset address as what? 0001. Next, 0001 means this is a hexadecimal form. So this how to write in binary form, that is nothing but offset 0000, 0000 and 000 and 0001. So now what is the value we are getting? Here is 0001, 0001, 0001, 0001 and 0001. And now in hexadecimal form, the value is what? 1111H. So how many bits total? 20 bits. So 16-bit address location which is converted into 20-bit physical address, that is the generation of physical address. That means segment address is shifted left by 4 times and add that segment address to the offset address. We are getting a 20-bit physical address. So here this process which is done by this summation is nothing but here physical address generation. Now let us see next one, segment registers. So here we have already seen different registers. So in these different types of registers, the first one is what? General purpose registers. Second one is what? Segment registers. So we have to see the registers one by one. All these are the different types of registers of 8086 microprocessor. The first one is general purpose registers. Here the general purpose registers are AX, BX, CX and DX. So AX is nothing but accumulator and BX is nothing but base register and CX is nothing but count register and DX is nothing but data. So all these are the different general purpose registers. Here each register is 16 bits. Each register is 16 bits. It stores a 16 bit of data. So AX is 16 bit. So if you divide this AX into AH, AL, that means X is a 16 bit, H is higher byte and lower byte. That means this is 8 bits and this is 8 bits. For example, I am taking move is an instruction AX, 1234H. So 1234H is a data which is stored in 16-bit register. So register is nothing but what? It stores some data. It stores some bits. So here 1234, it is a 16-bit data. How to write in a 16-bit form? So 1 is nothing but 0001, 2 is nothing but 0010, 3 is nothing but 0011 and 4 is nothing but 0101. Total how many bit? 16 bits. That 16 bits of data which is stored in AX register. In the same way, BX register is also for storing. Here CX register is nothing but, for example, if there is any loop, if the loop is rotated 4 times or 5 times, we have to give ch move ch comma 04. That means the loop is rotated 4 times. Okay, so that is based on the number of loop rotation. And next one is a data registers. So all these are 16 bit of size. So if we use the same register, if you store the same 8-bit data, you have to use move AH comma 12H or move AL comma 34H. So here these two are nothing but what? It's an 8-bit data. Okay. So next one is a segment registers. So how segment registers are nothing but what? Here all the segment registers are of size 1 megabyte of size. So whereas each segment is of 64 kilobytes of memory. And here the different segment registers are code segment, stack segment, code segment, data segment, and extra segment. So all these are the different segments. For example, if you take what is the use of this segment registers? For example, if you go to one colony, that colony which consists of total 100 houses. So all those houses are like 10 row or are arranged in 10 into 10. That means 10 rows and 10 columns. That means here all the houses are like this, 10 rows and 10 columns. Okay, 10 rows and 10 columns. So here these are not 10 by 10, the space is not sufficient if there is a 10 rows and 10 columns. For example, I have to go 20. So all the houses having numbering 1, 2, 3, 4, 5, 6, 7. So I have to go to 13th house. So all the houses having numbering. So we have to easily identify the house. So we have to go to the first, second row and third house. So that means easily identified the house. So in the same process, the segment registers are used to identify where we have to store the data and where we have to store the code. For example, if you take move AL comma 12H, move BL comma 34H, add AL comma BL. So these three are the different instructions. So here in this, each instruction, that means this is code segment and data segment. So here the code, this is a code, that means program. The program which is always stored in code segment. That means what is data? The data is nothing but the data which is stored in registers, that is the data. This data which is stored in data segment. That means we have to identify the data and we have to identify the code easily. So that is the use of segment registers. So stack segments are nothing but here in pointer and index instruction pointer. So here this instruction pointer are always points to the next instruction. So whereas extra segment is nothing but this is also one of the code segment we have to store after the memory is completed. We have to shift it to the extra segment. So that is the use of segment registers. Now coming to next one is the pointer and index registers. Here the pointer and index registers are nothing but SP is the stack pointer, BP is the base pointer, and SI is the source index, and DI is the destination index and instruction pointer. So here the instruction, here these two are index registers. That means source index and destination index. These two are pointer registers. So here the index registers are used as a normal general purpose registers as well as for offset storage in case of indexed, base index and relative base indexed addressing modes. So where we have different types of addressing modes which are available in 8086, we have to these source index and destination index, we have to use it for those addressing modes. Whereas the register SI is generally used to store the offset of the source data in data segment, while the register DI is used to store the offset of the destination in data or extra segment. So here the index registers are particularly used for string manipulation. These two index registers are mainly used for string manipulation. Now coming to flag registers. And the flag registers is also 6. So it is also a 16-bit register. Here see, this is a 16 bits 0 to 15. So here the flag registers, the first one is a carry. So these flag registers having the numbering and the flag is fixed. Here this is a 0, first flag is carry, and the next parity flag at second, auxiliary carry, 0, sign, trap, interrupt, direction and overflow. So here total flag register consists of total 9 flags. 9 flags. So these total flag registers which is divided into conditional flags and control flags. Conditional flags are 6 and control flags are 3. The 3 control flags are direction flag, interrupt flag and trap flag. So let us see one by one. So remaining all are don't care conditions which these bits are not used. So only these 9 bits are used out of 16 bits. We are using only the 9 bits. First we have to see the carry flag. So carry. So carry flag is nothing but this total flag register which depends on the output of the arithmetic and logical unit. So for example, the output of the logical unit which generates a carry. For example, see 1000 and 1000. So if you add these two, 1 plus 1 0, there is a carry. If this carry is generated means this flag is set. So first of all, what is a flag? So flag is nothing but it stores a single bit of data, either 0 or 1. Register is nothing but it stores a group of bits. So that is carry flag. Now parity flag. Parity flag is nothing but we have even parity and odd parity. So even parity is nothing but if the output which contains even number of ones, this flag is set. If this contains the odd number of ones, and here the flag is 0, that is a parity flag. Auxiliary carry. So the difference between the carry and auxiliary carry is, so if you add a 8-bit of data 0001 and 1000 and 0010 1000. For example, this auxiliary carry is nothing but if a bit which is generated from nibble is nothing but which is a 4 bits, which is 4 bits of size. The carry which generates from here to here, that this flag is set, auxiliary carry flag is set, otherwise it will be 0. That is auxiliary flag, 0 flag. For example, if the output of the ALU is 0, then 0 flag is set. Then sign flag. So here the most significant bit, that is positive sign or negative sign, based on the bit, this flag is set. Then trap, interrupt and direction flag. So here this trap flag is set. This processor enters the single step instruction execution. If the program is executed in a single step, then this trap flag is executed. Interrupt flag. So interrupt flag is set. Here there are the maskable interrupts are recognized by the CPU. That means any interrupts which is recognized by the CPU, this interrupt flag is set. The next one is a directional flag. This flag bit is 0. The string is processed beginning from lowest address to highest address. If this flag bit is 1, then the string is processed from highest address towards the lowest address. So this is about the different flag registers, and total 9 flags. Thank you. Now the operation of 8086 microprocessor is, so here I am taking one example, move AL, 06H and move BL, 05H and add AL, BL. So this is a small program. So this program which consists of instructions and data, that means code and data. Here the code and data which is stored in code segment and data segment. Here the code which is stored in CS and data is stored in data segment. So after storing this, so here it generates a physical address and the bits and the instructions which is going to first move instruction, move AL, 0H, which is going to this bus and it is stored in first byte. Here AL, 06H. So this 06 byte which is again sent to execution unit. So here the data which is traveled like this and stored in, here is AL, right? Here 06H is stored. After storing of this instruction, again the same process again repeats, and next byte which is stored in, that is BL, 05H. So again the 05H which is stored in this register 05H. After storing, what is the next instruction? Add instruction. So again we have to take the next instruction from the code segment and it is stored in instruction stream byte queue and it goes through the ALU. So this is an ALU which adds two different registers data. That means add. So in AL1 data is there and BL other data is there. So this ALU add those two. So if depends upon the output of the data, the flag registers are set and reset. And which displays the output which is always stored in accumulator, AX register. So for example, if the result is 6 plus 5 is 11, that means B. That B value which is stored in AX register. So this is the operation of the 8086 microprocessor. Thank you.